Friends, welcome to the tutorial series on network analysis made simple. This is a module-wise VTU network analysis paper solution series. In this tutorial, we shall solve module 2 of VTU network analysis paper of June-July 2018 of syllabus 15 EC 34. Friends, I prefer to emphasize on basic circuit concepts and strategy rather than detailed mathematical steps. I know you are already well equipped with the required mathematical skills. Hope this tutorial will ignite some of your thoughts. Let's go ahead. Friends, first let us answer question 1. In this question, we are required to state the superposition theorem and determine the value of Ix in the network shown in figure using superposition principle. We know that superposition theorem is applicable to linear networks. It states that in a linear circuit containing multi-sources, the response in any branch is the algebraic sum of the responses obtained by considering each independent source as acting separately, during which time the other sources are forced to zero. Remember, we are considering only independent sources each time. We also know that voltage source is forced to zero by short circuiting it and current source is forced to zero by open circuiting it. For example, in the circuit shown in figure, if Ix1 is the current due to only voltage source and Ix2 is the current due to only current source, then Ix is equal to Ix1 plus or minus Ix2 depending on the direction of currents we obtain. Friends, now considering only voltage source, current source is forced to zero by open circuiting it as shown in figure. Observe the network. The circuit has reduced to a single loop network. Note that. Hence, by writing the Kirchhoff's voltage equation for the loop, tracing it in the anti-clockwise direction, we get 2 times Ix1 plus 2 plus 1, 3Ix1 minus 10 is equal to 0. By solving this simple equation, we get Ix1 is equal to 2 amperes. Next, by considering only current source, the voltage source is forced to zero by short circuiting it as shown in figure. Let Ix2 be the current due to only current source. Observe the network. The network has reduced to a 2-junction node network. One junction node is V1 and the other is a reference node as shown. So, by writing the nodal equation for node V1, we get V1 by 2 minus 3 plus V1 minus 2 Ix2 divided by 1 is equal to 0. But Ix2 is equal to minus V1 divided by 2 or V1 is equal to minus 2 into Ix2. By substituting for V1 and solving, we get Ix2 is equal to minus 0.6 amperes. Therefore, Ix is equal to Ix1 plus or minus Ix2. By substituting for Ix1 and Ix2, we get Ix is equal to 1.4 amperes. Very simple, isn't it? Friends, next we shall solve question 2. In this question, we are required to obtain Thevenin's and Norton's equivalent circuits at the terminals A and B in the network shown in figure. We know that To find Thevenin's and Norton's equivalent circuit, we have to find Thevenin or VOC across A and B. Observe that Thevenin is the voltage across 5 plus J5 ohm impedance. Let I be the current through 5 plus J5 as shown. Observe that there are two parallel connected impedances, one of 5 plus J5 and the other of 10 plus 5 plus J5 across a current source of 5 angle 30 amperes. Using parallel branch theorem, current I is equal to impedance of the other branch divided by sum of the two parallel connected impedances into total current. By solving, we get I is equal to 1.58 angle 48.43 amperes. But Thevenin is equal to 5 plus J5 into I. By substituting and solving, we get Thevenin is equal to 11.17 angle 93.43 volts. Friends, to find Z Thevenin, forcing current source to 0 by open circuiting it, we get the circuit shown in figure. Observe the network. Now, the network has two parallel paths across the terminals A and B, one of 10 plus 5 plus J5 equal to 15 plus J5 and the other of 5 plus J5 ohm. Therefore, Z Thevenin is equal to 15 plus J5 into 5 plus J5 divided by 15 plus J5 plus 5 plus J5. By solving, we get Z Thevenin is equal to 4 plus J3 ohm. We also know that IN is equal to V Thevenin divided by Z Thevenin. By substituting the values and solving, we get IN is equal to 2.234 angle 56.56 amperes. Knowing V Thevenin, IN and Z Thevenin, the Thevenins and Norton's equivalent circuits drawn are shown in figure. Hope you understood it. Friends, next we shall solve question 3, in which we are required to find IL through the load resistance RL in the network shown in figure using Millman's theorem. We know that according to Millman's theorem, the given circuit can be reduced to, which I call it as, Millman's equivalent circuit across the load branch as shown in figure, where V equivalent is equal to summation of VI GI divided by summation of GI, and in our circuit, summation of VI GI is equal to V1 G1 plus V2 G2 plus V3 G3. By substituting the values, we get summation of VI GI is equal to 30. Similarly, summation of G equivalent is equal to G1 plus G2 plus G3. By substituting the values, we get summation of G equivalent is equal to 0.95 mho. Therefore, V equivalent is equal to 30 divided by 0.95, which will give us 31.578 volts. But R equivalent is equal to 1 divided by G equivalent, and hence R equivalent is equal to 1.05 ohm. Using V equivalent and R equivalent, the Millman's equivalent circuit drawn is shown in figure. Using the equivalent circuit, we know that IL is equal to V equivalent divided by R equivalent plus RL. By substituting the values and solving, we get IL is equal to 3.02 amperes. It is simple, isn't it? Friends, next we shall answer question 4 to verify the reciprocity theorem for the network shown in figure. We know that reciprocity theorem is applied to a single source linear and bilateral network. So, according to reciprocity theorem, the ratio of source to response remains same even after their positions are interchanged. Meaning, to verify reciprocity theorem for the given network shown in figure, we have to find the response Vx. Now, observe the network. There is one source and the response is Vx. Also observe that there are two parallel branches across the current source, one of 5 plus J5 and the other of 2 minus J2 ohm. Friends, to find Vx, we need to find Ix, and Vx is equal to Ix into minus J2 ohm. So, using parallel branch theorem, Ix is equal to impedance of the other branch divided by sum of the two parallel branch impedances into total current. By solving, we get Ix is equal to 4.642 angle 111.8 amperes. Therefore, Vx is equal to Ix into minus J2. By substituting the values and solving, we get Vx is equal to 9.284 angle 21.8 volts. Friends, to find Vy, by interchanging the positions of the source and the response, we get the circuit shown in figure. Now observe the network. The current source is introduced in such a way that it will drive the current through the capacitance in the same direction as that of the current source in the original position. This is very important. Also, observe that the two parallel branches across the shifted current source now are one of 2 plus 5 plus J5 and the other of minus J2 ohm. To find the response Vy, we have to find Iy, and Vy is equal to Iy into 5 plus J5. Hence, using parallel branch theorem, Iy is equal to minus J2 divided by 5 plus J5 plus 2 plus minus J2 into 5 angle 90. By solving, we get Iy is equal to 1.313 angle minus 23.198 amperes. Therefore, Vy is equal to Iy into 5 plus J5. By substituting the values and solving, we get Vy is equal to 9.284 angle 21.8 volts. Since Vx is equal to Vy, the reciprocity theorem is verified. Hope it is clear to you. Friends, next we shall answer question 5, in which we are just required to state and explain maximum power transfer theorem. Friends, we know that the amount of power transferred from source to load depends upon the type of load and the type of source and its impedance. Further, the condition of maximum power transferred from circuit to circuit differs. For example, consider the circuit shown in figure, in which the supply circuit and the load circuits are identified. We know that IL is equal to Vs divided by Rs plus RL, Note RL is varying. But power transferred to load P is equal to IL squared into RL watts. By substituting for IL, we get P is equal to Vs squared into RL divided by Rs plus RL whole square. But we know to find the condition for maximum power transferred, we have to find dP by dRL and equate it to 0. Therefore, using U by V form of differentiation, dP by dRL is equal to denominator into differentiation of the numerator minus numerator into the differentiation of the denominator divided by the denominator square. Friends, by equating dP by dRL is equal to 0, we get only this numerator part which will be equal to 0. Hence, by equating dP by dRL equal to 0, we get RL is equal to Rs. Therefore, the maximum power transfer theorem states that if the source is DC and the load is pure resistance varying, then the maximum power is transferred to the load when load resistance is equal to the source resistance. To find the maximum power transferred, we know P is equal to Vs squared into RL divided by Rs plus RL whole square. By substituting Rs is equal to RL, we get P max is equal to Vs squared divided by 4 times RL. Hope you got the skill of answering such descriptive questions. Friends, finally, to strengthen your basic circuit concepts and develop your thinking process, I suggest you go through my textbooks, Network Analysis Made Easy, CET Handbook, Linear and Integrated Circuits and Applications, Basic Electronics, and Basic Electrical Engineering, which are available online. Thank you for watching this video.